So here's another question involving the hydrogen atom, and again we're given the energy of the energy levels in joules. So they've been nice to us, we won't need to convert these from EV to joules to do our calculations. And the first question, again, nice and simple. What happens when a hydrogen atom is ionised? Well, any time an atom is ionised, it's involving an electron being removed from the atom. Nice simple starting question for you there. Then it says, state the minimum amount of energy in joules required to ionise hydrogen from its ground state. So what that's asking is it's saying if you've got an electron sat here in the ground state and you want it to be able to be ionised to leave the atom, it's got to make it to the point where the energy is equal to 0 joules. Or it's got to gain an equal amount of energy to its negative potential energy. So in this case here, in order to be able to give an electron enough energy to just get to 0 joules, you have to give it 2.18 times 10 to the minus 18 joules. And because it says state, you can see it's not expecting you to do a calculation. It is literally just 2.18 times 10 to the 18 joules. So that is the energy that I need to ionise. Now it's saying that an atom is excited to the n equals 3 energy level, and as it does that, it might emit either a single photon or 2 photons. And the question wants you to describe what's happening in each case. Well, again, if we go back up to our energy level diagram, it's at the n equals 3. If it's going to give off just 1 photon, that means we have 1 transition. So it's going to go all the way from the n equals 3 down to the ground state there, giving off a photon of energy equal to the difference in those energies. If it's giving off 2 photons, then it's going to do that in 2 stages. It's going to go from n equals 3 to n equals 2, and then it's going to go from n equals 2 to the ground state. And so that's what we have to put in words as the answer to that question. So what happens to the electron in each case? Well, for 1 photon, we have the situation where the electron emits a single photon equal to the energy difference in levels between n equals 3 and the ground state. But for 2 photons, the electron drops first to n equals 2 by emitting a photon, and then it drops from n equals 2 to the ground state. The next question says, use the diagram above to identify the transition which produces a photon of energy 2.09 times 10 to the minus 18 joules. So what we're looking for is the step in energy between energy levels that will give us 2.09 times 10 to the minus 18. Now everything here is in terms of 10 to the minus 18, so this makes life a little bit easier because we're looking for a change that gives us 2.09, and we can pretty quickly, now I can see straight away that these energy level transitions are going to be far, far too small. So I'm going to be looking for something going down to the ground state. And if I start from the beginning, if I take an electron dropping from the n equals 5 all the way down to the ground state, I have an energy level difference of minus 0.09 times 10 to the minus 18 minus bracket minus 2.18, and that gives me an energy of 2.09 times 10 to the minus 18 joules. Hurrah! I have found the answer straight away. So the transition that produces a photon of that energy is the transition from the n equals 5 to the n equals 1. Finally, it says, what is the frequency of an emitted photon due to a transition from level n equals 2 to the ground state? Well, the change in my energy levels, which is going to be the higher energy level minus the lower energy level, is also equal to, and we're looking for a frequency here, so I'm going to use HF as my energy. So n equals 2 to the ground state is going from minus 0.54 times 10 to the minus 18 to minus 2.18 times 10 to the minus 18. So my change in energy is minus 0.54 times 10 to the minus 18 minus 2.18 times 10 to the minus 18. And when I plug those numbers in, I will get my energy. But I'm not going to do that just yet, because if I rearrange delta E equals HF, I just want the frequency here. So my F is equal to delta E over H, Planck's constant. If I plug this energy in for my delta E, and I put 6.63 times 10 to the minus 34 in for H, I end up getting a frequency of 2.47 times 10 to the 15 Hertz. And that's about the order of magnitude that I would be expecting to see.